Asha, I think you're good to go.
Yeah, I think it's time to get started. So, hello, good evening, a very warm welcome to all. It's a wonderful day, and I feel privileged to extend my warm welcome to all present here. Thank you for joining us today's webinar on the topic Grid Modernization by Mr. John D.McDonald, conducted by IEEE MEA SBC Student Branch Chapter. Just a little housekeeping before we get started. To keep the quality of sound functional during the meeting, please mute your throughout the meeting unless instructed. If you have any queries during the presentation or after the presentation, please type them into the chat box. And at last, feedback form of this webinar will be provided at the end of the session. So please make sure each one of you are filling the form after the webinar for availing the certificate for the same. Now, without further ado, I'm inviting Ms. Nida, Program Committee Coordinator of PES Student Chapter, for welcome speech. Over to you, Nida.
Hello, am I audible?
Yes, Nida, you are.
Hello everyone and welcome to today's section on grid modernization, technological advancement beyond smart grid. I'm Nida, Program Committee Coordinator at IEEE PES MEA SBC. First of all, I'd like to introduce today's chief guest, Mr. John D.McDonald, the former president of IEEE PES and Smart Grid Business Development Leader at GE's Grid Solutions, who will be giving us an insight to smart grid modernization. He holds an MBA in Finance from University of California, Berkeley, and BSc and MSc in Power Engineering degree from Purdue University. Also, our honorable guest is an international power engineering expert, industry personality, and IEEE leader whose remarkable career spans over 49 years. He had published 150 papers and articles, co-authored 5 books, and has won US patent. He received the honors IEEE Millennium Medal, IEEE PES Meritorious Service Award, also an outstanding electrical and computer engineering award from Purdue University, and many more. Thank you, sir, for taking time out and being here today. We are so proud to get such a desirable and right speaker for our session. Now, I would like to welcome IEEE Chairperson, Mr. Mohammad Mushraf, Councillor Jamshid sir, PES Chairperson Ms. Safa, Advisor Dr. Febina Bibi. Last but not least, I welcome all IEEE XCOM and PES XCOM members, and for those of you just joining us from different parts of the globe, welcome all. And now I'm handovering the section to the keynote speaker, Mr. John D.McDonald. Sir, please.
Thank you. Why don't I'll bring up my slides, okay, so we can start. Let's see. And can you see my slides?
Yes, sir. The slide is good.
Okay, I'll put it in slideshow mode. Can you see it? Can you see it?
Yes, sir. Yes, sir. This was visible.
And did you see it change?
Yes, sir. It's next slide down.
Okay, so everything is working okay, right? All right.
Yes.
Well, listen, I wanna thank you for the opportunity. I really, I really enjoy supporting students and young professionals, and particularly student branches, and really want to make sure all our student branches are successful, and spend a lot, want to spend a lot of time helping all the students, especially at the universities, have very good programs, and also have membership growth, increase the membership of your student branch. So one of the things that is very important to me is not just participating in IEEE or the Power and Energy Society, but taking leadership positions. You get more value out of IEEE and the Power and Energy Society if you lead, if you have a leadership position. So I'm an IEEE Life Fellow, but I've had a number of positions. One in writing standards in substations, the substations committee chair, been doing that for 35 years. As you guys said, former IEEE Power and Energy Society president, 2006 and 7. The IEEE Board of Directors, which was Division 7 Director, 2008 and 9. The IEEE Standards Association Board of Governors. And I've been a distinguished lecturer for IEEE Power and Energy Society for over 20 years. The one thing that is very exciting for me is that this is my 50th year of being an IEEE member. Okay, 50 years. I joined IEEE as a second-year university student in 1971. So, and I've been working 46 years full-time in electric power system automation. So, on the right here, though, is something that is very important to me and should be very important to you guys. You really want to have a balanced work and life. You want to do well with your schooling or your work, but you also want to have good health, take care of yourself. And so this is my actually my 11th year of working out with a trainer, personal trainer, running 5K races. And the top right picture is my son. When he finished his MBA at Duke University, we ran the 5K trail at Duke University. Lower right is my trainer. We had just finished a 5K race. We took second in our age groups, and he was a professional athlete. He was a professional American football player. So I stay in good health. I'll be 70 this year, but I'm in better physical health than many people much younger than I am. So it's very important to me to do well with work or school, but also take good care of yourself. Okay. These are the topics I'll talk about, and if you have any questions, don't be shy. I love hearing your comments and questions. So keep those in mind, and when we finish, we'll have time for questions. Okay, but these are the topics I'm going to touch on, and the reason I call this grid modernization is that's really the new term that we use for smart grid. And when I say technological advancements beyond smart grid, I want to talk more about the future. Now, what's very important is key industry societal trends. These are the things that are happening in the world around us. And particularly as students or young professionals, it's very important to realize we're transitioning from devices and systems to holistic solutions. In other words, don't just focus on the microprocessor-based device or the system, but each of those has two-way communications, and think how we can put those together into a much bigger solution. And I'll show you examples of 6 solutions here in a minute. Holistic means company-wide, not just for one group in a company, but company-wide. Holistic means enterprise-wide. Success is technology, standards, and policy. Okay, I say success is like a 3-legged stool, a 3-legged stool with 3 legs, right? If one of those legs is weak or missing and you try to sit down, you will fall over. You won't be successful. Same here with what we do. If one of these areas is weak or you haven't focused on it, you won't be successful. The technology must be standards-based for interoperability, and policy is the strongest incentive to a customer to buy my technology. We're really focused today on grid flexibility and particularly self-healing. I'll show you logic I can put out on the electric grid that can automatically detect a fault, locate a fault, isolate the fault, and restore service upstream and downstream of the faulted segment within a minute or two with no human involved. And also resiliency. We have so many extreme weather events that stress the grid. How can we make the grid more resilient? And that's a real focus area today. And what I'll talk about here in a little bit is it's caused us to do more with microgrids, strategic microgrids with an electric utility that makes their grid more resilient. We'll talk about big data and what we call the journey to digital transformation. Many components today of an automation system are cloud components. They're cloud-based in the public cloud. And I've really been focused on social media and how we can use social media to accelerate the restoration of electricity after an outage. People really prefer to interact with their electric utility with social media, not with telephone anymore. And what I'd like to see is my electric utility take my Twitter handle and put that in my customer record. And I would prefer to interact with my utility with tweets. And the utility knows my address and my home based on my Twitter handle, and they can bring up my customer record, okay? And then what's very important today is a convergence of the IT part of the utility organization, information technology, and the OT part, which is operations technology. We need a seamless working together of IT and operations for enterprise data management, okay? So again, if we stay on that same topic, grid modernization really requires IT-OT convergence, okay? Bringing together IT and OT. And one important point that I want to make here is before we think about a smart grid, we need to make sure we have a strong grid, okay? Strong grid before smart grid. And strong grid means the communications infrastructure and the IT infrastructure, okay? If we buy some new stuff and we install it, we're depending on the foundation, the infrastructure, to be able to support things like response requirements, bandwidth requirements, and latency requirements. And if we have a weak areas in our foundation, in other words, we don't have a strong grid, we won't get the performance that we expect out of the new things that we're buying, okay? So part of the strong grid is the IT infrastructure, and the other part is the communications infrastructure. So convergence of IT and OT is very, very important. It actually gives us the ability to empower consumers to manage their energy use and save money without compromising their lifestyle with in-home enabling technology, right? Things like smart thermostats, things like Alexa, things like energy saving switches that we can plug into the wall that can turn lights on and off, and also to be able to optimize the integration of more renewable energy and have broader penetration. The one thing that we're doing is there's much more focus today on the distribution part of the grid, okay? So, I've been working now full-time almost 47 years in adding intelligence to the grid. So the term smart grid to someone like me is not new. I've been doing this for a long time. So I like to call this a smarter grid, and what I've been doing for many, many years, and many others too, is shaded here in light gray. And the smarter part of this, what we're doing more recently, is shaded in light green, the smart grid additions. So you can see on the bottom here, I have voltage control shaded halfway. The reason is voltage is directly proportional to load. And if a utility is like a very hot summer day, and it's a summer peaking utility, and they don't want to exceed their previous peak, what we can do is lower the secondary voltage, and that lowers the load. Voltage is directly proportional to load. And again, we've been doing this for a long time. We can also switch capacitor banks on the distribution feeders to reduce losses, right? That's power factor control or VAR control, reactive power control. But what we've done in the past is we've done these separately. Now we're doing these coordinated with each other. We call integrated volt VAR control. So the right part of this is light green is the integration of voltage control and reactive power control. What's on the left here in light gray is power factor control by itself, and load management or voltage control by itself, okay? We'll talk more about renewable generation in a minute. If we go up here to the second row, you can see sensors here is shaded halfway. You know, we've been adding sensors to the grid for a long time. What we have today, though, is what we call specialized sensors. For instance, this one I show here is a monitoring and diagnostic device that I would take the oil from the main tank of the transformer and put it through this device on a continuous basis. And this device will look for dissolved gas in that oil, called dissolved gas analysis, or DGA, because we have devices today that can detect up to 9 different gases in the oil of the main tank of the transformer, and the presence of a specific gas is a specific failure mode that's occurring in the transformer. Okay, it's very, very important. So we look at, is that gas present, and how, and what's the rate of change of that gas being generated? You know, because if it's failing very, very quickly, then we're going to see much more of that gas being created much, much faster. Okay, so we have a lot of specialized sensors today that we can put on the grid. This is distribution management. This is the computer-based control system that manages the complexity today of the distribution system. We call this a distribution management system, a DMS, or an ADMS, Advanced Distribution Management System. If we go downstream of the substation, we have what we call distribution automation. This is where the strongest benefits are to the electric utility, is on the feeders, the distribution feeders. And then we'll talk about smart meters here. Okay, so a lot going on the grid. But I mentioned holistic solutions. And holistic, again, is company-wide or enterprise-wide. And a solution is a set of technology components integrated together to successfully interoperate to meet the business needs of the customer. Okay, so think about this. The question is, you have a lot of technology components. How do you put those together to create a holistic solution that provides value to the customer? Okay, and here's examples of 6. Asset optimization, where we focus on critical, expensive assets on the grid. And the first one is transformers, right? And the second one is circuit breakers, high voltage and medium voltage circuit breakers. So we have today what we call remote monitoring and diagnostics, M&D, and we also have what we call APM, asset performance management. And I would say this probably right here is the second strongest business case today. As you know, the strongest business case is here in distribution optimization. So we have asset optimization, we have demand optimization, where we aggregate load, customer load, and we can use that to with generation dispatch. So we can use that in the control center. When load increases and frequency drops, we want to bring the frequency back to the scheduled frequency. Normally what we do is we ramp generating units to do that, but it may be a lot less expensive to pull the trigger on some aggregated load. Okay, here we're implementing smart meters and the two-way communications with metering. We're going to spend a lot more time in this talk on distribution optimization. There's transmission optimization, and one of the things we're doing here is getting more value from synchrophasers, right, from phasor measurement units. You know, the synchrophaser can give us like 40 to 50 samples per second of what's happening on the grid, where the traditional data we use is every 2 to 4 seconds. Okay, and then lastly is workforce and engineering design optimization. I know in many places in the world, like the U.S., I'm in Atlanta, Georgia, in the southeast part of the U.S. And if we look at the U.S. as an example, in the next 5 years in the energy industry, 40% of the employees, not just engineers, but employees, and 60% of the executives will retire. Okay, that's a lot. And one thing that's important is the work that we do is an art, not a science. There's a big difference between an art and a science. If it's a science, we could all read a book and do it, be the best, right? But that's not what we do. What we do is an art. What we have to do is read the book to learn the science, and then spend many years with experienced people to truly know how to apply the science in the real world, okay? And that's why so many companies and I just started in the IEEE Power and Energy Society a mentoring program. Why mentoring programs are so important. You know, students, young professionals, you need to spend time with experienced people to learn the art of what we do from the experienced people before they retire, okay? So that's why we have so many mentoring programs. Also, that's why a couple of years ago, I put a talk together called Key Insights to Career Management. It's not a technical talk, but I looked at over my 46 years of my career, and there were 12 key decisions I made that influenced the rest of my career. And I talk about those 12 key decisions in a 1-hour webinar that the IEEE PES, it was so popular that the IEEE Power and Energy Society recorded it one time when I gave it. And it's a webinar, 1-hour webinar that's available for free on the IEEE PES Resource Center called Key Insights to Career Management. And I really encourage all of you to spend an hour, watch that webinar, and you'll learn a lot about how to get the most out of your career and the decisions that you should be making, okay? So if we take these 6 holistic solutions and we put a technology roadmap together, you will see that in the upper left here is the office and the control center. In the lower left are substations. Lower middle is downstream of the substation on the distribution feeders. And you can see what I mean by we're transitioning from components and systems, devices and systems, to holistic solutions. So just take a look at the light blue boxes. That's the distribution optimization holistic solution, light blue. These are software applications, these 4 blue boxes in the office. These 2 blue boxes are systems, distribution management system, outage management system. The lower left, substations. You see the substation controller. You also see applications. So what we're doing is we're distributing the intelligence. It used to be that all the intelligence was in the control center. We call that the centralized approach. Everything was centralized in the control center. Now we're taking some of these applications like fault detection, isolation, restoration, and integrated VOLVAR control, and also running those at the substation level, okay? And then on the feeders, we have switches and breakers. We need switches here to support the logic in fault detection, isolation, and restoration. And VOLVAR devices here, we have capacitor banks and voltage regulators, and they support the logic of integrated VOLVAR control. So think about this. All these blue boxes could be from different vendors, but they all have to be able to communicate successfully with each other and exchange information. And this is what we mean by interoperability, and why the compliance to the same standard or sets of standards is very important. Now, the 2 key words that I keep mentioning over and over again is integration and interoperability. For a grid to be truly resilient, there's 5 key systems, 5 key components and systems that the utility must invest in. 1 is smart meters. 2 is the metering two-way communications called automated metering infrastructure. 3rd is geographic information system, GIS. 4th is outage management system, or OMS. And 5th is the distribution management system, DMS. Smart meters, of course, give us meter readings that are used to generate bills, but we also ping some of these smart meters to get the voltage that we put into the DMS. Because when we do VOLVAR control, we're flattening the voltage profile and then lowering it on the distribution feeder. But we want to make sure that the voltage at the customer at the end of the feeder is within the standard for that country. You know, like in the United States, it's 120 volts plus or minus 5%. Well, 120 minus 5% is 114 volts. I have to make sure the voltage at the very last customer on the feeder is above 114 volts. So I can check that by pinging certain smart meters for voltage, okay? And then all smart meters have a capacitor in them that stays charged, and when that meter has an outage, there's enough charge in that capacitor for one final communication of that meter upstream to the utility saying, you know, I just experienced an outage and this is the time it occurred. We call that last gasp communication, okay? The geographic information system here is the reference system for the network model for OMS and DMS for these two systems. We take status changes from the DMS and we make sure we bring those into the OMS. Why? Because let's say a feeder breaker trips and this entire feeder now is de-energized. We send that status change that the breaker now is open to the outage management system, and it knows, based on the network model, all the customers that are fed from that feeder, and it knows now these customers have an outage, okay? Then I talked about, with customers, we want to move from using the phone to interact with the utility to social media, okay? So let's talk a little bit about microgrids and distributed generation. So at the bottom of the slide here, distribution controls and protection were traditionally designed to take advantage of electricity flowing in one direction on the distribution part of the grid, from source to load. What happens when we integrate distributed generation? We now have electricity flowing in two directions, from source to load and also from the distributed generation upstream, okay? Now we can integrate renewable energy at the transmission level, at the distribution level, or at the end user level, right? With photovoltaic panels on the roof of the home of the end user. So when we integrate distributed generation, we create a much more complicated situation for the distribution part of the grid. And it creates challenges for us. Things like open circuit over voltage due to unintentional islanding. We could have protection ratings that don't match our fault currents. Okay, why? Because when we were doing our protection study, we did a short circuit study to find out what are the fault currents that we expect in a fault, so we know how to set the relays. When we did the short circuit study, we assumed a source side contribution only, not a load side from the distributed generation. So our protection ratings may not be correct. Also, the fault currents from the distributed generation vary because the distributed generation is intermittent. The sun isn't always shining all the time. The wind isn't always blowing all the time. So it's very intermittent, okay? And we'll talk about stress on voltage regulation equipment in a minute. This is an example of a microgrid with industrial and residential load. And this happens to be a very rural village, okay? This is like a village not near any electric utility. So it has its own diesel generation. This is its base generation, but it has hydrogen fuel cells, it has PV panels, and it has low head hydro generation. So we took a microprocessor-based relay and added logic to it to become the microgrid controller. And its objective is to make sure this residential and industrial load is satisfied all the time, but to make most use out of the hydrogen fuel cells, the solar generation, and the hydro generation, and minimize the use of diesel, right? The diesel fuel is very expensive, and it's very expensive to transport that to a rural village. And when the diesels operate, they emit carbon dioxide to the atmosphere, okay? So this is examples of some microgrids that were installed in the United States, in Philadelphia. And this was an old, what we call Philadelphia Navy Yard, where the the United States Navy used to build and repair large ships, okay? And when that Navy Yard closed, it became an economic development zone. And we worked together with the electric utilities there, the Philadelphia Electric Company, PECO, and also the Regional Independent System Operator, PJM, to put in a couple microgrids. And in addition to the microgrids, each one has an automation control system. We also implemented a DMS, which we call a distribution SCADA system. SCADA, supervisory control and data acquisition, and a control center and a network operations center to manage the grid there at the old Philadelphia Navy Yard. Okay. Oh, by the way, this GridLab D is open source software that was written by one of the U.S. Department of Energy laboratories, the Pacific Northwest National Lab. This is available for free, and it's software to model the electric grid on a full three-phase unbalanced basis. So there they use GridLab D for modeling and analysis, and again, it's open source. Okay. How do we manage, though, the intermittency of distributed generation? I said the sun isn't always shining and the wind isn't always blowing, and we need what we call bridging storage, right? Energy storage that bridges the intermittency, right? When the sun isn't shining, the load still needs to be satisfied. So maybe we have lithium-ion batteries, energy storage, that kick in instantaneously for support. For longer-term needs, we have now fast start thermal generation that's typically natural gas fired, and it's very fast starting and fast responding. Okay. Now we also have something new. I said we're distributing the intelligence, and I said, you know, we're taking applications from the control center and running them at the substation level. We're also distributing intelligence to the edge of the grid, and we call these grid edge controllers. Okay. And it's so we have a combination of grid edge controllers and microgrids that are occurring now downstream of the control center. Okay. And we call these low voltage network because they're installed on the low voltage network, dynamic because they're doing continuous set point control, grid edge controllers. I wrote this article. This is available online in 2013. And what I did was I have the voltage waveforms in the article from a distribution feeder in San Diego, California, San Diego Gas and Electric. Over 35% of the homes on this one feeder had rooftop solar panels. That's a very high penetration. These homes were along the Pacific Ocean and had what we call a marine layer of fog. Marine meaning due to the ocean. So the humidity, the humidity from the ocean would cause fog in the morning, and that fog would burn off as the day went on. Well, when that fog would burn off, all of these homes began generating at the same time, and the voltage would spike and then oscillate as the sun went in and out from behind the clouds. Well, the load tap changer, what we call a substation transformer online tap changer here, its job is to keep the secondary voltage constant no matter how the primary voltage is fluctuating. And you know, the more volatility there is on the grid, the more this tap changer has to operate. This is a mechanical controller, so the more it operates, the less life it has, right? So this tap changer on this feeder, before any customers installed rooftop solar panels, was operating 5 times a day with an expected life of 35 years. Now with over 35% of the homes with rooftop solar panels, the volatility was so great, is so great on this feeder, that this tap changer is operating over 120 times per day. Its expected life now is less than 2 years. It'll have to be replaced. So the object of my article was to talk about new applications of power electronics. We need a power electronic based tap changer. We can't use we can't use mechanical control devices anymore on the grid as the penetration of renewables grows. Mechanical control devices don't make sense with the volatility that we have on the grid. So I wrote this article in Power Electronics magazine with 3 new applications I talked about. The online tap changer. The second one was what I just talked about, low voltage network dynamic grid edge controllers. And third is what we call smart inverters, increased capability from inverters. Okay? Now, we still have a lot of challenges in the integration of renewables, what we call impediments, challenges. We're still learning as we go. For instance, there's a lot of unobservable distributed generators behind the fence. In other words, the electric utility, they may have third-party companies that are connecting distributed generation to their grid. By unobservable, we mean there's not enough data coming from those distributed generators to the utilities so they know what's happening, so they can observe what's happening. Okay. We also have enablers, things that we've learned. We're doing better forecasting now, and I mentioned we have the thermal fleet. In other words, the new natural gas-fired generation has higher quick starts and can respond more quickly to changes in frequency. Okay, but if I'm in a utility and I'm studying the impact of wind or solar, I always want to do modeling and analysis of that impact. I want to simulate it. And these are, just with wind, these are wind study references that our energy consulting group at GE have done for many, many utilities around the world. Okay, you always want to simulate and study the impact. So this is what we call the Advanced Distribution Management System, right? This helps manage the increasing complexity of the distribution system. This is the centralized approach. So this would be in the control center. And within the shaded box here is the system, the ADMS. And this is what we call centralized control, as I said. Everything is happening at the control center. There's really 2 parts to this system. There's a basic SCADA system, supervisor control and data acquisition, and then the applications to model the grid. The reference system for the network model is the geographic information system, and we get all the data from the substation and feeder devices coming in to the system. These applications analyze it and optimize it, and then control commands go back down to the field to do the optimization. So there's three sets of applications on an ADMS. This is the real-time set of applications. And if this is an area you're interested in, another fellow and I, we did a 1-day tutorial just on this subject for the IEEE Power and Energy Society. And at the beginning of COVID, a year ago, the IEEE Power and Energy Society made our 1-day tutorial free. It was available for free to any IEEE PES member. It's 5 different PowerPoint modules, and it's a 1-day tutorial on this subject. So this is the real-time group of applications. This is the on-demand applications used for analysis, okay? And then these are a third group called ancillary or extra applications. So one of the things we do in the tutorial is we go through each of these applications in detail in terms of what they do, okay? Now, every utility, their goal is a fully digitized grid, or what we call here digitally enabled. But no organization can get there in one step, okay? So what we do is we help utilities put a roadmap together, like say, where are you today? Okay, you're at the manual control and legacy methods. You have a manually operated network, static view of network configuration. Well, let's add SCADA, let's add trouble calls, and let's add circuit reclosers, and that will give you 28% lower customer minutes interrupted than the base level. In other words, it tremendously helps their reliability. Whoops, the reliability of the grid. Then we can go to automation and visualization by adding distribution automation, network visualization tools, and outage management prediction analysis. 43% now lower customer minutes interrupted from the base level And then ultimately the digitally enabled with asset performance management, outage analytics, and network optimization utilization, now greater than 50% lower customer minutes interrupted, okay? So again, what is the appropriate roadmap for each organization? But each step in the roadmap must provide significant benefits back to the organization, okay? Another way to look at this too is, let's say a large utility has 856 distribution circuits and they want to improve their reliability. That's a lot of circuits to automate. That would be very, very expensive. But we don't need to do that. Let's study these circuits. Let's model and study these circuits in more detail. And we find that only 200 of the circuits, only 23% of the circuits, account for about 3/4 of the total outage minutes of that utility. So 23% of all the circuits account for 71% of the total outage minutes. So what we do is we invest in automation of just 200 circuits, not all 856. Much better use of money and a much greater return on investment, okay? So the other thing for utilities to get more benefits from investment is there's several different types of data in a microprocessor-based device. The data that we're more used to is the operational data. This is what the operators use in the control center to monitor and control the power system. Things like voltages, current, loading, status of circuit breakers, alarms, things like that. These are points. What we could realize more benefits from is the non-operational data. This is the primary user is not the system operator in the control center, but somebody else in the utility. Could be engineering, could be maintenance, power quality, asset management. Now, I introduced these concepts in the IEEE Power and Energy magazine in 2003. Today they're industry standards, but I first introduced these because I was doing many projects and I said, you know, we're not really taking advantage of this non-operational data. This is points and points and files. This could be the digital waveform from a relay, could be a sequence events report, which would be a file, could be dissolved gas and oil for maintenance. You know, there's about 25 to 30 other groups in the utility, in addition to the operators in the control center, that want this data. So if we compare it, the operational data is typically time sequenced at the scan rate of the control center of the master station, typically real time or near real time. And we use industry standard communication protocols to communicate that information. Non-operational data is a points or a file, mostly historical. And if it's a file, we may need a vendor-specific proprietary format to extract it, okay? So I think one thing that's exciting for us is what we call the Internet of Things. You know, we're taking intelligent machines, connecting them with big data and analytics, and with people. No matter where the people are, any way we can connect at any time for intelligent operations. So what we're doing is this is called the next productivity revolution, figuring out how we can leverage this to create more value. So what we're doing is, you know, if you look at any organization, particularly utilities, on the left here is the situation that currently exists where each group, like the protection group, the planning group, they have their own systems, devices, and databases, and there's really no sharing. What we want to do on the right here is break down those silos, break down those walls between the groups, and have a federated data mart that brings together all the data sources in the enterprise so that there truly is sharing. What we would have on the right here in light blue or cyan is all the different data sources. We would have looked at those and extracted all the data that has value. And in green here on the right is all the different users, operational and non-operational users, that now have the data they need to provide value to the organization. So What's really exciting is this journey to digital transformation. And if I was a student today, I would not only study the power system, but I would also study what we call data science. We're hiring data scientists today, both at GE, at suppliers, as well as utilities, because so much of what decisions we make are being driven by data. And I have 5 books that I've co-authored. One recent book is called Big Data Application in Power Systems. And I wrote the first chapter of that book called A Holistic Approach to Becoming a Data-Driven Utility. Okay? So you can see on the lower left here, we started really with reactive. We weren't using data. What we were doing is waiting for something to fail, and then we reacted to it. Not a very good way to operate an organization, right? Wait for something to fail and then react to it. So then we became responsive, and today we're more predictive. We're taking health information from assets. That's that asset optimization holistic solution we talked about. And we're trying to predict all the failure modes of an asset, whether it be a transformer, high voltage circuit breaker, medium voltage circuit breaker. We don't want things to fail, right? We want to address a potential problem before it gets to the failure point. But this is only halfway on the journey. By using artificial intelligence, by using machine learning, and the concept of the digital twin, we want to get to prescriptive and eventually to autonomous, truly self-healing, self-provisioning, and extensive autonomous operations with limited human intervention. This is what's so exciting today. Okay, but one thing that's very important is industry standards. This is the smart grid conceptual reference model we developed some years ago, and we've now updated it in the last couple of years. And I was part of a group of 25 industry experts that did that, and in the last couple of years, part of a group of 11 industry experts that updated this and modified it. Okay. But we went through hundreds of standards, industry standards, and we published these 16 as being the foundational standards for smart grid. These are the standards. If whatever project you're doing, if you're developing a product like a GE, or if I'm at a utility wanting to buy equipment, these 16 standards cover all of smart grid. And we say smart grid goes from turbine to toaster, right? From the power plant to your home. That's generation, transmission, distribution, and the end use customer. And these 16 standards cover that, that landscape. Okay. Now, what's nice today is we have one standard in the world for control center to control center communications. Makes it very easy today. We have 2 standards basically from control center to field equipment, what we call IEEE standard 1815 or DNP3, Distributed Network Protocol 3, used primarily by North American suppliers. European suppliers still use IEC 870-5, 101 for serial, and 104 for network communications. And within the field, the worldwide standard is IEC 61850. But in North America, we still use a lot of DNP3. So let me wrap up here with a few lessons we learned from deployments, and I'll highlight just a few of these. And then we can have questions. Okay. One thing that is very important is a holistic solution is a set of technology components. The maturity of that solution is only as mature as the least mature component. Remember now, if you take a chain with links, right? A chain is made up of links. The chain is only as strong as its weakest link, right? When you pull the chain. So you need to make sure that all the components here of your holistic solution have the same maturity, okay? Otherwise, what we had to do is we had to field re-engineer or upgrade some of the components to meet the objectives and expectations. Number 2 here is industry standards. I said 2 key words, integration and interoperability. You know, think of those light blue boxes on the technology roadmap from different vendors. They all have to successfully communicate with each other and exchange information with each other. We do a lot of testing of the equipment before it goes to the field. It's much easier to repair it in the factory rather than in the field, okay? And you want to do end-to-end testing from the device in the substation all the way up to the office and the control center. What's very important here is project management. For each smart grid project, the one project manager must have multidiscipline authority. There's so many groups within the utility that are involved in these projects. The project manager must have authority over all these groups. What we really found was the you know, how important project management was, because we found that, you know, we as a vendor, we could provide the utility the best technology in the world, and they could have the best engineering team in the world. But if a project manager wasn't very good, the whole project could fail. So we really need to build an A team here with project and technical members, because there'll be challenges to collectively solve. So the very best, not only engineering or technical people, but project people, okay? And then a major stakeholder today in what we do is the residential commercial customer. For many years with smart grid, we were only concerned with the grid, right? Everything upstream of the meter. And now with smart meters and in-home enabling technology that we talked about, a new major stakeholder is the end-use customer. And that's very, very important. We spend a lot of time now learning more about the end-use customer and taking that into account. So let me finish there. Thank you very much. We have about, I think, 10 minutes for questions. And what I'll do is I'll stop sharing. I'll stop sharing here. And come back to the there. Come back to the screen. Now I can see everybody again.
So,
oh, let me turn my
insights with modernization. So with that, we'll go ahead and take some time for questions. You can type your questions into the chat box now.
Okay. If anyone has any questions or things that you may be working on or things you may be interested yourself, even about IEEE, about IEEE PS, about my career. If you have any questions for me about you know, about or mentoring programs, or you know, any comments or questions you have, please don't be afraid to ask.
Guys, we have a very good chance to ask all the questions. Please ask all of your questions. Please put them in the chat box. It looks like we have some of the questions, sir. The first question is
about the mentoring program. Right now we're piloting the mentoring program with about 29 mentees and some mentors. But I'll tell you, Joshua, if this is something you're interested in, find me on LinkedIn. Well, let me just say, one of the things I talk about in my key insights to career management, one thing that's very important for all of you is to be active in LinkedIn. You need to prepare a very good profile for yourself that's as detailed as possible, because companies today pay, the HR in companies, they pay LinkedIn and they do keyword searches of everyone's profile. And that's how they find candidates for jobs, okay? Now, I mentor many students, and I mentor many young people, and many people have reached out to me through LinkedIn, had questions about their career, had questions about choices they need to make, and things like that. Don't be afraid. Reach out to me through LinkedIn. Be happy to connect with you. And if you have any questions about your career, things that you're doing, you can ask me on LinkedIn. Okay. The IEEE PS mentoring program is just now getting started. We're going to take it from the pilot program and expand it, but it's going to be some time, before it expands. So in the meantime, find me on LinkedIn, and don't be afraid to reach out to me on LinkedIn. Okay. Oh. Question, yeah, do we expect 100% renewable? That would be a challenge. I talked about some of the issues with intermittency. Think about if we were 100% renewable and the wind stopped blowing and the sun was behind the clouds, all of you would still want electricity at your homes, right? So where would that electricity come from? So some of the technical challenge is dealing with the intermittency. Here we get into energy storage, and I also said we get into like natural gas-fired turbine generators that start quickly and respond quickly. So what we're seeing today is new technologies that help us. And let me give you an example of one that's only been available for a couple of years. GE announced a couple of years ago a new electronic gas hybrid turbine generator. And it's a packaged solution of 10 megawatts of lithium-ion batteries and a 50 megawatt fast start, fast responding natural gas-fired turbine generator. There's software that optimizes the integrated operation of the batteries and turbine generator. Southern California Edison in California has installed 2 of these already. So this is just some ideas of new technology solutions that we've all come up with to help us with increasing penetration of renewables and how we deal with the intermittency. Okay. We do expect customers to do more control at the customer level. I said we're distributing the intelligence. We have grid edge controllers that we install now, low voltage power electronics that we're installing just outside your home on the feeder to your home. But we do expect customers to do more control and provide more. We have an IEEE standard 2030.5, which is the new standard for smart inverter communications and communications to the end use customer to provide that customer the data they need with the technology that they would have to be able to respond to real-time pricing on the grid and to truly optimize and manage their energy use. Privacy of information is extremely important. So in addition to, we have cybersecurity and we also have privacy of information. So we're doing we have a lot with private. We've been working actually with privacy of information for quite a while, and there's a privacy by design model that was developed by the Privacy Commissioner in Canada, in the province of Ontario, Canada, that's been adopted by the International Association of Privacy Professionals. So we actually took this model and we included that in the smart grid equipment that we supplied to a Canadian utility for smart grid. And I have a report on how we operationalize privacy by design in a smart grid project. That's public information. If any of you are interested in that, let me know. But it is extremely important. I give a separate talk on cybersecurity, and I talk about the Ukraine, what happened in the Ukraine when 225,000 people were without electricity. And we've learned a lot about how to to address many of the vulnerabilities that we could potentially have. So cyber attacks, we've learned a lot from attacks that have occurred, and I think we're doing a much better job now. We also, like at GE, we have a product development life cycle flowchart that has cybersecurity at every step of the development. So one thing with developing products is you have to include cybersecurity from the very beginning. So there is a link to, if you go to the website of NIST, the National Institute of Standards and Technology in the U.S., and look for the link to the Framework 4.0 document. NIST, I helped the U.S. government. There were 11 of us selected by NIST in the U.S. government, smart grid experts, to help NIST put together a document on what the future smart grid technology would look like. We forecasted out 10 to 15 years, and it's about a 250-page document with many diagrams. And this is all public information. It's all available on the NIST website. If you have trouble finding it, let me know. Okay, but it's a very, very good document in terms of the future of smart grid. All right, so I think we're a little bit after the hour, so we reached our end point.
It looks like we have covered most of your questions. Please do connect with to LinkedIn or mail, sir. And now, thank you, sir. Thanks a lot. We have come to the end of our webinar, and I cordially invite Ms. Maharin, Member Development Coordinator of PES Student Chapter, for a word of thanks. Over to you, Maharin.
Okay, Isha, am I audible?
Yes, you are. Please go.
Hello.
Yes, you are.
Okay. Am I audible?
Yes, Maharin, please go on. Proceed.
Okay, thank you. So, good evening, everyone. Myself, Mehri, Membership Development Coordinator, IEEE PES MEA SBC. It's my pleasure to propose a vote of thanks on behalf of IEEE MEA SBC. I would like to thank our chief guest, Mr. John D.McDonald, for such a wonderful and informative session for us on grid modernization. We want to express our gratitude to Honorable Chief Guest, who has spared his precious time for us and graced this occasion with his presence. Thank you so much, sir.
You're welcome.
And I would like to thank our PES advisor, Dr. Febina Bili ma'am, also PES chairperson, Ms. Safa Khalid, and all the PES members. Thank you, everyone. And also, I thank all the participants for your presence and patience. Thank you so much. Thank you all.
That's great. Thank you, everyone. And we appreciate you being here. The feedback form is in the chat box. Please make sure you are done it for the certification. Please make sure you are done it. And the link is in the chat box form. And we all appreciate you being here. Thank you so much, sir, once again. Thanks again for joining us for today, and we will see you next time.
Hey, good luck with your student branch. I wish you tremendous success with your student branch, and let me know if I could ever help you in the future also. Okay?
Sure, sir. Thanks. Thank you, sir. Thanks a lot for your valuable time. Thank you, sir.
All right. All right. Bye-bye. Bye-bye, everybody.
Bye-bye. Take care, sir.
Thank you.
Thank you, sir.
I request all the participants, please fill the feedback form in the chat box, and you can leave the meeting window. Please fill the feedback form, and I request all the participants, you can leave the meeting window. That's it for the day, and we'll meet you soon again. Please ensure yourself you have filled the feedback form. I have posted it in the chat box.
So webinar is officially finished, and you can start to leave after filling the feedback form. Thank you.
Thank you for all your patience and being over here for the day. You can please leave the meeting window. I request all the participants, please leave the meeting window and ensure yourself you have filled the feedback form. I request all the participants can leave the meeting window. Thank you for joining for the day. Let's meet again soon. I request all the participants, please leave the meeting window and please ensure you have filled the feedback form. Thank you all for joining once again. Thank you guys for all your valuable presence. I request everyone, please leave the meeting window. Yeah, Aisha, anything?
No. Just it was a mistake.
Okay. Yeah, XCOM 2 can leave. XCOM 2 can leave. You can leave yourself. I request everyone, please leave the meeting window. Thank you. Yeah, stop it, the recording. Please stop the recording. You could have stopped it early.